Today, let's talk about representer theorem. It is essentially the reason why the support vector machines and the smoothing spline have the same form, that the nonlinear function is a sum of kernel functions. So here is the statement of the theorem. Suppose we are given an optimization problem over function f. The objective has two terms. The first term is a finite sum of the loss function. The second term is a regularization term. Then this optimization problem has a minimizer f star that has a form as a combination, the summation of the kernel functions. Throughout this series, we have already seen two examples, the smoothing spline and the SVM. Both of them can be written down in the representer form for the optimization. Then it also has this form for the solution as a sum of kernel functions. So first, let me write down the objective and the solution for the smoothing spline and the SVM in the representer form. So for the smoothing spline, we have the loss function as the mean squared loss. So that will give us yi minus f of xi square. Then the norm is the second derivative square dx, right? So for this norm term, we can also write it out as the L2 norm. So this thing also equals to the L2 norm of the second derivative, right? You can write it out as so this is an operator act on f, and then we have the L2 norm here. Okay, if we just compare the objective to the representer theorem, you see that the loss function here for the smoothing spline is a squared loss. Then for the second term here, I should say that this h here stands for RKHS. It is the reproducing kernel Hilbert space. So this is a space that can be defined by this kernel function, right? So the kernel function can define the RKHS, right? So see that this function, the function with this form are the elements in the RKHS. So that's what it means. So the norm here for the representer theorem is a wide class of norms. The L2 norm is a special case of it. So this can be written down as the Hilbert norm for the function f, right? Then for the smoothing spline, the kernel function is the cubic spline kernel, right? That has the form of x minus xi to the third power. So this is the smoothing spline. Now let's look at the SVM. For SVM, we have the loss function as a hinge loss. So that has the form of max 0 and 1 minus yi f of xi. So you have the hinge loss plus the second term will have the lambda times, right now I'm just going to write out the Hilbert norm here first. Okay, I also forgot the lambda in here. So recall that in our SVM video, this f function here is defined in the feature space as W transpose phi of xi. Then this Hilbert norm here is defined simply as the Euclidean norm for this W vector, right? So and when this is infinite dimension, so this W basically behaves like an L2 norm. Then for the SVM problem, we also convert this into a dual problem, right? So we convert this into a dual formulation. And then that admits the final function f star of x equals to summation of the kernel function, right? So see the difference in here that for the smoothing spline, we actually have a specific form for the kernel function that is caused by the curvature penalty, right? We use variational calculus to solve it. But for the SVM, you see that we only penalizing on the weight here, right? That is separated, that can be factored. The f can be factored into weight times the feature map. So these have no interactions. That's why we can freely choose our kernel function for the SVM problem. Okay, so now let's actually look at the proof of this theorem or a sketch of the proof of the theorem to see why it makes sense. Okay, now let's talk about why the representer theorem is true. So let's just use our smoothing span, for example. So suppose we are given some data and we want to fit a smooth curve to it. Right? Suppose this is our data and using the smoothing span, suppose this is a final fit of the curve that we have. Okay, so now I'm gonna draw another function here. So let me just for this function, I'm just gonna fix the values on this evaluation points, right? I'm just gonna fix these blue dots to be the same as the green curve. But I'm going to add more terms for this function, right? So suppose that our function looks like this. So we can actually write this function f here as two parts, right? So our intuition just says that this blue curve will not be preferred because it just simply add more complexity to the fit without any gains, right? Because we have the same values at those evaluation points. So that means the first loss function, the loss function stays the same between the two curves, but the complexity is being penalized by the second term. So that's why we have the green curve preferred here. So if I'm to write this down, I can actually write down for each function f into two parts, right? So the f, I can decompose that into f0 plus f1. Then I can say that f0 of xi equals to 0 for I goes from 1 to n, right? So see here that the blue curve can really be added, right? So we have kind of a f0 function here, right? Just add to it. So we have the 0 at each evaluation point, right? We have the evaluation point, then we just have a very complex function at on top of that for this blue curve, right? We have a complex function on top of that, but this additional function f0 here actually is not good for the fit, right? Because we don't have any gain in the first term, but we compromise the second term. Okay, so now we can actually assign two orthogonal space to this function, right? So we can say that f0 lives in the space of E, or E orthogonal. Let me just say is E orthogonal. The f1 lives in the space of E, right? So this E here will become the kernel span. And then the part that is perpendicular to the kernel span will all be killed because it add no values to this optimization problem. So okay, so now for the function f1. So using our intuition of the smoothing span here, the data actually acting as a force that is bending our curve. Because without any data, our curve will just be a flat line, will be a straight line without any bending. So that's why the solution of fx end up having is a sum of the kernel functions that is kind of centered at each data point, right? We have the x minus xi to the third power at each data point because we only have the force at each xi, right? And we only need n data points, n number of the kernel functions, right? We don't really care about like what's in between them, right? So that's why we don't have like a random function somewhere in between here another kernel function. We don't need that. That add no values to this optimization. We only care about what's going on in the data points. And then the kernel function here is actually acting like a basis function for our final fitted function f of x. So that is a key intuition for the representer theorem. Okay, so now let's think about what does the representer theorem tell us about the support vector machines. So in practice, when we want to fit the support vector machine to practical problems, the process can feel a little backward. So remember that in our derivation process, we started with primal problems on the feature space and derived the dual problem, and that reduced it to a quadratic programming problem that involves a kernel function. So in practice, so all we need to do is to pick a kernel function first. So this is a practical SVM fit. So the first step is that we want to pick a kernel K. And then we can use QP, the quadratic programming, to solve for alpha. So we use QP to solve alpha. And the step three is to obtain the function, right? We define the fx directly using the representer theorem that give us as alpha I k x xi. And then we also have the affine term b here. That can also be solved. Then we can make the prediction uh, as you can define the decision boundary as this equals to 0, right? So the prediction will be the sine function of f of x. So that is how we fit the SVM in practice. We start by picking out the kernel without thinking about the feature space phi of x. So here are three examples that I copied from the package of the scikit-learn. It compares between three different kernel choices for the SVM. So first we have the linear kernel, right? So that means decision boundary is just a sum of linear functions. So we have this. We also have this linear function, linear decision boundary on the input space here. Then the RBF kernel and the polynomial kernel have those nonlinear decision boundaries you see here, right? So it seems that the RBF kernel have a better decision boundary compared to the polynomial. It is more flexible. This is due to the local behavior of the RBF kernel. So that is the most common choice for the SVM classifier when we use in practice. We mostly just use the RBF kernel for classifying the real problems. So actually, the main point I want to say here is that because the representer theorem, you can just pick a kernel without considering what's going on in the feature space or the optimization problem. We can just select a kernel that has the behavior we want and fit our classifier to it.